All right, folks, welcome back to the plenary for late this morning or this afternoon, wherever you are. As we saw yesterday, there is some really outstanding work being done by students. This is something that we can all be very heartened by and really leads us to have great hope for the future of our community. We're going to see more examples of that today in these student lightning talks. So I'm going to pull up each slide. I would like the student to then share their screen, or rather to not share the screen, excuse me, to activate your video and your microphone and give your presentation. So we're going to start out with Neal Bassett from the University of Colorado Boulder. Neal.
Thanks. Hi, everyone. My name is Neal Bassett, and I am one of the members of the team working on the DAPPER mission, which you heard about earlier today from Jack Burns, and Administrator Bridenstine also gave us a shout out yesterday. So the main goal of DAPPER is to measure the low-frequency observational signatures from hydrogen in the early universe, so from the dark ages and cosmic dawn when the first stars and galaxies began to form. So I work on the data analysis side of the project. So we've created an analysis pipeline that's based on pattern recognition to analyze these low frequency observations. And so my poster is about a method that I've been working on for ensuring that the results that we get from this pipeline are robust and how we can know that we have sufficiently modeled each component of the data for these low frequency experiments. So again, my name is Neal Bassett, and if you're interested in this really exciting field of cosmology and astrophysics from the far side of the moon, please come and visit my poster. Thanks.
Thank you. Next, we have Aisha Khatib from the University of Maryland. Aisha.
Hi, can you hear me?
Yes, we can.
Okay, great. Hi, everyone. My name is Aisha Khatib. I'm a first-year PhD student at the University of Maryland. I study geophysics and planetary seismology. The project I'm presenting in my poster involves the passive seismic experiment package on the Apollo 11 mission and discusses how we can use anthropogenic or human-caused events as seismic sources to characterize the lunar subsurface. Apollo 11 seismic experiment is pretty unique in that there's only a passive component, there's no active component. And also because
on this paper.
And also because the astronauts set up the seismometers partway through their extravehicular activity, or EVA. This means that a lot of the astronauts' unrelated activities after they set it up, for example, collecting core tube samples, loading equipment, or jettisoning equipment after the EVA, would register on the short period seismometer. And instead of looking at these spikes in the seismic signal as noise, I use it to try and build a seismic velocity profile of the subsurface of the landing site. This presents pretty interesting challenges, such as how to determine what events are, where they originated on the lunar surface, and how exactly to calculate time differences between their origin times and their seismic event times. It's an interesting experiment to see whether it's possible given the constraints of the equipment and data collection on Apollo 11. I hope all of you stop by. Thank you all for listening, and I hope you have an excellent rest of conference. Thank you.
Excellent, thank you. Next, we have Vanessa Lowry from the University of Central Florida.
Everyone hear me? Excuse me. Hi, my name is Vanessa Lowry. I'm a PhD candidate at the University of Central Florida. I'm currently working with Dr. Carrie Donaldson-Hanna on linear spectral unmixing in the thermal infrared. I've written an algorithm for the weighted least squares algorithm, which is basically a chi-square minimization, and also implemented a sum to one constraint on that, where the abundances all sum up to 100%. I applied this to the OSIRIS-REx blind study data, which are primitive asteroid analogs, mixtures, and real meteorites. And we unmixed with a full spectral library of fine particulates in a full and limited spectral data range. Basically, we're trying to show how effective a linear model would be on fine particulates that exhibit nonlinear behavior. So please come visit my poster tomorrow, and I look forward to meeting you. Thank you.
Thank you. Next, we have Nivedita Mahesh from Arizona State University.
Hi, my name is Nivedita Mahesh. Can you hear me okay?
Yes, you're coming
Yeah.
through fine. Thank you, Nivedita.
Yeah. Hi, my name is Nivedita Mahesh, and I'm a fourth-year grad student at Arizona State University, working with Professor Judd Bowman. My primary research focuses on analyzing various aspects of the Far Side Array, a radio telescope designed for the radio quiet zone of the moon. In this work here, I present some tangible results from the notional array layout, which includes investigation of various layouts that could mitigate artifacts in the image, to designing a strategy that could enable dual polarization measurements with the array. This strategy involves directly embedding the two polarization receivers in the tether as the rover traverses its path. This would result in the two orthogonal antennas being offset from each other. Thus, I've carried out a feasibility study of non-co-located antennas in an array. The importance of this work lies in the fact that dual polarization measurements would help the science cases of the far side by decreasing the integration time and differentiating the host star signal in case of exoplanet studies. I hope I've sparked enough curiosity to encourage you to stop by poster number 56 tomorrow. Thank you.
Very good. Thank you, Nivedita. Next, we have Realtor Nakano from Auburn University.
Can you hear me?
Yes.
All right. My name is Realtor Nakano. I'm a first-year PhD student working with Dr. Hirabayashi at Auburn University. Tomorrow morning, I'll be presenting our work on asteroid Phaethon. Most of you may know what the Gemini meteor stream is, which is the meteor stream that you can observe in December. And Phaethon has been considered as a meteor, as a parent body of this meteor stream. And here in the work, we investigated the structural sensitivity of Phaethon and found that it is sensitive to structural failure regardless of the bulk density condition at the current rotation state, requiring some amount of cohesiveness. This is consistent with the recent observations which revealed dust tails. And more importantly, we also find that Phaethon may be much more sensitive in the past due to faster rotation, which implies that the large-scale mass shedding process can be triggered, which can be a source of the Geminid meteor stream. And for more information, I poster tomorrow, and the poster ID is 100, so it should be easy to remember. And again, I'm Nakano, presenting mass shedding activities of asteroid Phaethon. And bye. Thank you.
Thank you. Next, we have Katarina Slabochinska from the University of Central Florida. Katarina.
Hello, so I'm Katie Slabochinska, and I work for Dr. Christopher Bennett at the University of Central Florida. And I'm going to be presenting a poster on spectral effects of carbon-bearing species during the space weathering of airless bodies. So understanding the effects of space weathering is essential to asteroid characterization due to its oftentimes drastic effects on their spectra. Most of us here are probably familiar with the spectral effects of space weathering seen on lunar soil caused by submicroscopic metallic iron formation, but a wide range of other spectral effects have been observed during space weathering simulations of carbonaceous chondrites specifically, including sometimes spectral brightening and bluing. So constraining and understanding how different variables can affect such spectral changes in carbonaceous chondrites during space weathering is going to be vital, especially now as Hayabusa 2 and OSIRIS-REx are working on bringing back samples from dark carbonaceous asteroids. We've designed an ultra-high vacuum chamber for simulating space weathering on regolith samples that will include multiple irradiation sources, heating and cooling capabilities, and an optical setup for collecting diffuse spectra in the visible near IR and mid IR with a geometry similar to RELAB. We are planning to simulate space weathering on both carbonaceous chondrite meteorite samples, as well as simulants of them produced here at UCF in the X lab, so we can control mineralogy and organic content. This experimental design will hopefully enable us to selectively control many variables that can affect space weathering processes and therefore systematically constrain their effects. If you're interested in hearing more or discussing this with me, please come see my poster, which is number 89 tomorrow.
Thank you so much, Katie. Next, we have Keith Tauscher from the University of Colorado at Boulder.
Hello, everyone. My name is Keith Tauscher. I work with Jack Burns at the University of Colorado Boulder. I'm a soon-to-be graduating graduate student, and I work with him on the Dark Ages Polarimeter Pathfinder, which is DAPPER, which he talked about this morning. And I basically designed the data analysis pipeline for DAPPER with the help of a few others. And really the main problem that we have to solve in that, like for the data analysis to measure this 21 centimeter global signal to learn more about the early universe, is to look through the galactic foregrounds. So the foregrounds are 4 to 5 orders of magnitude larger than the signal. So we really have to use pattern recognition to separate out the foreground from the signal. And my poster is about our method for making this as easy as possible. So it's easier to separate the signal and foreground when they look more different in the data. So basically we have two different methods of making the foregrounds and signal look differently. So the signal is the same for all time bins, and it also appears only in total power polarization, whereas the foreground appears differently in every time bin and it appears in all polarizations. So basically how we measure the data using this dual dipole antenna allows us to measure polarization and time dependence. And my poster is about how we use those two things to help in the separation. So come check out my poster tomorrow if you want more information.
Excellent. Thank you, Keith. Next, we have Gavin Tolometti from the University of Western Ontario.
Hello, everyone. Can you hear me?
Yes, very well.
Excellent. So, hello, my name is Gavin. I'm from the University of Western Ontario and the Institute for Earth and Space Exploration in London, Canada. And my poster, using temperature constraints to identify potentially traversable permanently shadowed regions at the lunar South Pole, builds off the work by Sargent et al. 2020 when they were trying to study the trafficability of regolith within PSRs. And we know ever since water ice deposits have been detected in some PSRs in the South Polar region, future robotic and human exploration missions have been proposed to prospect and potentially mine this material. But we knew little information about whether these robotic platforms could actually traverse on the regolith. We didn't know much about whether they were strong enough to hold rovers that we've been designing, or whether they'd be stronger than regolith we can actually see through videos and images from the Apollo days. So from Sargent et al. 2020, where they were able to peer into the shadows using secondary illumination scattering off of opposite crater walls, they were able to study the bearing capacity of the regolith using boulder tracks so they could find within and outside PSRs. And they discovered with certain thermal conditions that the regolith is potentially traversable for robotic platforms. So we use diviner annual and maximum temperature data to constrain these temperature conditions and narrow down what PSRs that are greater than 0.15 kilometers squared could potentially be traversable for robotic platforms. So if you would like to learn more about where we could send robotic platforms to look for water ice deposits, come see our poster number 73 tomorrow morning.
Excellent. Thank you, Gavin. So clearly we have some fascinating presentations ahead of us at the next poster session.